Good afternoon. We are reaching for the end of our season of seminars, and today we are very pleased to welcome Professor Joan Brennecke. She is currently Cockrell Family Chair in Engineering in the McKetta Department of Chemical Engineering at the University of Texas at Austin. Her research interests are primarily in the development of less environmentally harmful solvents. These include supercritical fluids and ionic liquids. In the developing of these solvents, Dr. Brennecke's primarily interests are in measurements and modeling of thermodynamics, thermophysical properties, phase behavior, and separation. Major awards include the 2001 Hypatia Prize from the American Chemical Society, the 2006 Professional Progress Awards from the American Institute of Chemical Engineers, the J.M. Brosnett Awards at the 11th International Conference on Properties and Phase Equilibrium in Greece in May 2007, the 2008 Stiglitz Award from the American Chemical Society, the 2009 E.O. Lawrence Award from the U.S. Department of Energy, and the 2014 E.V. Mercy Award in the Industrial and Engineering Chemistry from the American Chemical Society. She has served as the editor-in-chief of the Journal of Chemical and Engineering Data since 2010. Her over 200 research publications have granted her over 20,000 citations. She was inducted into the National Academy of Engineering in 2012 and recently served as the chair of the National Academy's study on a research agenda for a new era in separation science. So welcome, Professor Brennecke. Thank you so much for being here. Please feel free to start your presentation.
Thank you very much for the introduction and most importantly for inviting me to participate in this absolutely amazing seminar series that you have held. So that's fabulous. I guess let me try, I can share. Okay, you can see everything okay?
Yep.
Okay, super.
Thank you.
All right, so what I'd like to talk about today is some work we've been doing lately trying to get a better understanding of ion dissociation in ionic liquids and ionic liquid solutions. And as just sort of an outline, I'll start out by talking a little bit about what we mean by ion dissociation and what the traditional, if you will, way is of calculating this ion dissociation, which people kind of call ionicity in ionic liquids, and then introduce the approximate method that we've been using and show what the results are using that approximate method for pure ionic liquids, aqueous solutions of ILs, and non-aqueous solutions. Most of the work that I'll be talking about today has been done by one of actually my very first totally University of Texas graduate students. His name is Oscar Nordness, and he just defended his PhD thesis 2 weeks ago. And he's now going to be going on to the University of California at Santa Barbara to do a postdoc with Professor Rachel Siegelman. Much of what I'll discuss, or some of what I will discuss, can be found in this review article that was just posted a few weeks ago from Chemical Reviews on ion dissociation in ionic liquids and ionic liquid solutions. So as we all know, we think about salt dissolution in water as being promoted by the hydrogen bonding interactions. For instance, hydrogens in the water interacting with the anions and the oxygens in the water interacting with the cations. And in fact, this is causing the dissolution of the solid crystal. In fact, this is just something I took from you can see the website, Middle School Chemistry. So something that we're all used to from our early learnings. In addition to the cations and the anions being solvated by water and being hydrated by the water, here shown as a solvated sodium and a solvated chloride. We can also have ion pairs that are held together by those strong electrostatic forces. People have categorized these ion pairs in many ways. They're the contact ion pairs or solvent separated ion pairs and so on. And ion pairs for conventional salts are more prevalent when you have very highly charged ions, right? So if you've got divalent, trivalent cations or anions, you've got that higher point charge, if you will, so that those electrostatic forces are stronger, keeping the pair together. These ion pairs for conventional salts in aqueous solutions is usually not very important for monovalent ions, except for something like lithium, which is so small, right, that it still has a very high point charge density. So we might want to think about ion dissociation and ion pairs as an equilibrium. So I just wrote down here for potassium chloride, you might have an equilibrium between a ion pair versus the solvated ions, and you might want to describe that by an equilibrium constant. But of course, we know that that wouldn't actually be concentration, that would actually be, you know, the equilibrium constant. These would actually be the activities of the cation, the anion, and the ion pair. How do we want to now start thinking about this for ionic liquids? Now, in ionic liquids, the cations and the anions tend to be multi-atom, in fact, very large cations and anions. So in most cases, the charge, whether it's on the cation or the anion, tends to be distributed across more atoms. And so making this just distributed charge would likely reduce the amount of ion pairing, right? Because you don't have those high charge density areas. On the other hand, we know that many of the cations and anions used with ionic liquids actually have things like long alkyl chains. And so now you've introduced another opportunity for attraction between the cation and the anion. So those attractions from between the hydrophobic parts of the ions, those alkyl chains, might actually increase the amount of ion pairing. So then we have to start thinking about, what about when we go not from an aqueous solution, but all the way to a pure ionic liquid? So in a pure ionic liquid system, you know, how do we define what the ion pair would be if all we've got is ions, all right? And in this case, no ions are solvated because we don't have a solvent. So are there really any free ions? And the answer, of course, is yes, because even pure ionic liquids conduct. So we know that there are free ions in pure ionic liquids. But this makes us really think about how do we visualize ion pairing, not just in IL solvent mixtures, but what happens as the concentration increases all the way from a dilute IL in a solvent, which could be water or could be something else, all the way to pure IL. Now, the way that people generally think about this in ionic liquids is in terms of a Walden plot. And a Walden plot is just a plot of the log of the ionic conductivity, all right, as a function of the log of the inverse viscosity. So all a Walden plot is really telling you is how conductive is an ionic liquid or an ionic liquid solution? How conductive is it for its viscosity? And people frequently compare it with the what they describe as the ideal case, which is this dashed line here, with the idea that the ideal case would be mostly dissociated. This is for actually 0.1 molar potassium chloride, which is not completely dissociated, but that's all right. You can see here that many of the ionic liquids are less conductive than potassium chloride for a given viscosity. So that's the normal way people look at it. But that actually brings up the fact that we frequently will think of dissociation as a, I'm looking at a picture. Is the cation and anion together, or are they apart? But it's really a dynamic process. And this is something that was emphasized by Professor McGinn, who you had speak with you earlier in your seminar series. And this is work that he did a few years ago, looking at through simulations, what do we call an ion pair? And so you could say, okay, we've got this cation in the middle, and the closest anion is the red one. And time passes, and the closest one is still the red one. But then more time passes, and the red one has moved a little bit away, and now the closest one is the yellow one. And so he used that to define an ion pair lifetime in an ionic liquid. He also looked at, we could think about an ion cage lifetime. So if you just draw a circle around the anions that are in the first, if you will, shell around the cation, and say that that's your initial ion cage, and then time passes and everybody moves a little bit. In the center, no anions have left or entered, so that ion cage has maintained its integrity over that amount of time. But then as more time passes, you can see that the red one has in fact left the cage, and the yellow or orange one has entered the cage. So in this case, you could define this ion cage lifetime. And what they showed was that diffusivities and ionic conductivities, which of course can be calculated from diffusivities, correlate with this ion pair and this ion cage lifetimes from molecular dynamic simulations. So the reason I bring this up is just to try to remind everybody that when we talk about ion dissociation, it's not a static picture. It's a dynamic picture, and we're really just looking at an average over time if we talk about how dissociated is an ionic liquid. So, so this is the way that people normally, because we don't, have the luxury of being able to calculate. It's more difficult to calculate activities than, if you will, concentrations. So people just describe this dissociation in ionic liquids as this ionicity, which is a ratio of the free ions to the total ions. So you're just at any given time, or averaged over time, which fraction of the ions are free, if you will, and which ones are paired. And to get an idea of this, people will use conductivity measurements, right, from electric impedance spectroscopy to measure the conductivity, all right, which is the transport of the ions, and say those are the free ions, and then use pulse field gradient spin echo NMR to measure self-diffusion coefficients. So the self-diffusion, which gives you the movement of everybody, right? So the NMR measurement is measuring the movement of, all cations, all anions, whether they are paired or free. So we can use that as an estimate of everybody, the total ions. So taking that ratio is what people traditionally use to describe ionicity. So as I said, the free ions, this is measured by conductivity measurements, usually electrical impedance spectroscopy. And you just need to have a little cell and and put electrodes in there, and you can back out the ionic conductivity. And it's a relatively quick and easy measurement if you've done this. And the NMR, like I said, you're getting the diffusivities by NMR, and then using those diffusivities with the Nernst-Einstein equation to get the molar conductivity of everybody moving. All right, and taking that ratio. So doing that, here's some results from the literature. And this is for a series of dialkyl imidazolium bis-triplamide ionic liquids, so pure ionic liquids, where they change the alkyl chain length from methyl to octyl. And so the methyl-methyl imidazolium bis-triplamide, using this method, has an ionicity of about 75%. So about 3/4 of the ions are free, all right? But as you increase the alkyl chain length, that ratio goes down, so that for the octyl methyl one, it's almost down to about just 50% of the ions are free. So now the problem with this method is that the conductivity measurements are fast, but if you've ever done the NMR experiments, they're rather tedious. And of course, you have to have the appropriate instrumentation. So we were wondering, is there a way to do this more easily? And so this was actually suggested by Luke Simoni, one of my graduate students with Mark Stadthair back at the University of Notre Dame almost 10 years ago, where he said, well, you know, let's just, instead of using NMR to get diffusivities, let's just use Stokes-Einstein. It's not perfect, but you know, this way we could get an estimate of the diffusivity just from measurements of viscosity. And of course, measuring viscosity of ionic liquids is a lot quicker than doing the NMR measurements. Now, the disadvantage of this is that we need to have some estimate of the size of the cation and the anion. So if we do this, then we're just putting in for, instead of measuring the NMR diffusivities, we put in the Stokes-Einstein equation, and things nice cancel out. And so we just need the size of the cation, the anion, and the viscosity, so that then this ionicity now just depends on the viscosity, the conductivity, the density, because we got to know the concentration, right? The density, and then some estimates of the size of the cation and the anion. So that's what I'm just trying to emphasize here, that now we're going to have very quick experimental measurements, and density, viscosity, and conductivity. There's a lot of data in the literature for those properties. So we can take data from the literature and estimate what this ionicity is. So the size thing. So there's many, many different ways of trying to estimate the size of the cation and anion. And so we just did the easiest thing we could possibly think of, which was just to use UNIFAC. So we're just using a group contribution method to get the dimension. And so this is assuming it's a sphere, right? You know, the cations and the anions are not spheres, all right? So this is the biggest part of this approximation, is using this group contribution method to get the size of the cations and the anions. Nonetheless, it seems to work out okay. And so, so this is the same data that I showed you earlier with the dialkyl imidazolium bis-tripplamides, where we have the values estimated from NMR, which is the blue over here. And then if we instead use viscosity data and UNIFAC estimates of the size of the cation and anion, it's not bad at all. All right, so we clearly get the trend of decreasing dissociation with increasing alkyl chain length. And the absolute values are not even all that wrong, right? So we thought this was pretty reasonable. And here is the same dialkyl imidazolium bis triple mid data, but just showing you that another way of thinking about this dissociation is in terms of these ET30 values, which is sort of the polarity of the ionic liquid. And so you have greater dissociation of the ionic liquid if it's more polar. Okay, so now we're moving on to taking density, viscosity, and conductivity data from the literature and calculating this ion dissociation. And so here, once again, I'm showing the ion dissociation as a function of alkyl chain length on the cation. In this case, it's for pyridinium cations. And the green is for bis triple mid anion, and the red is for dicyanamide. And so you can see that the bis triple mid with the pyridinium cation behaves just like the dialkyl imidazolium. As I make the alkyl chains longer, they don't like to dissociate because you're getting that van der Waals interaction between those alkyl chains. But interestingly, if you've got a anion that has greater point charge, greater charge density, right? The bis triple mid has the charge very much spread out across the anion. If you take dicyanamide, you don't get this alkyl chain length dependence. So in that case, it's that charge on the anion is dominating what's happening and decreasing the impact of the van der Waals interactions, the importance of the van der Waals interactions between the alkyl chain lengths. Here's another one with data from the literature. And so these are all bis triple mids, but the thing I have circled there, the kind of the I don't know, light yellow and the sort of pinkish color ones, what those are is a dialkyl imidazolium versus a trialkyl imidazolium. So if you block the acidic hydrogen in the C2 position, right, so the trialkyl imidazolium, then the dissociation increases. So you're cutting down on the interaction between the acidic hydrogen on the cation and the interaction with the anion. So you block that and it becomes more dissociated. And so that's a very clear trend. The other ones shown here, the blue, the green, and the red, those are just taking the alkyl pyridinium and putting a methyl group on two different spots. You can see it doesn't make any difference. So no effect of the position of the methyl group on those pyridiniums. All right, so here's keeping everybody with the same anion, right? The bis triple mid, so the very charge distributed anion with a series of all kinds of different cations that we could find in the literature with relatively similar alkyl chain lengths. And you can see that the dissociation goes from what we have on the left, about 60% of the IL is dissociated to the one on the right where 80 or 90% is dissociated. And that corresponds with the polarity as indicated by the ET30 value. Now, one interesting thing is if we look at the effect of the alkyl chain length on the anion, and this is for sulfate. So methyl sulfate all the way up to octyl sulfate. And you can see that here, there's almost no effect of the length of the alkyl chain on the cation. And I suspect this is because there's so much happening with the sulfate that the sulfate interaction with that acidic hydrogen on the imidazolium is what's really dominating the dissociation in the association, if you will, in this IL. Here's keeping the cation the same and changing the anion. And so you can see we go from something where we have an acetate all the way over to things like tetrafluoroborate and hexafluorophosphate. And if you've got something like an acetate, then it really, you know, very strongly interacts with the cation, so that the dissociation is quite low, all right, into things that don't interact very strongly with the cation, and the dissociation is much larger. All right, effective temperature. So if you looked at the folks who have calculated the ionicity, the ion dissociation by NMR, you would conclude that as you increase the temperature, the ion dissociation was going down. All right, so that's what's shown here as the open symbols in both cases. As you increase the temperature, it looks like the dissociation, the dissociation is going down. However, it's been noted in the literature that the measurements of diffusivities by NMR suffer from convection as you increase the temperature. So that those measurements are actually not very good, right? And that is reflected when we look at our estimates of ion dissociation from just the density, viscosity, and conductivity, where there's very little effect of temperature on the ion dissociation. So we think the values estimated from viscosity are actually better than what you would think from NMR because of this convection effect. All right, so what about when we've got an IL in a solvent? And of course, the first one we'll talk about will be aqueous solutions. So of course, with ionic liquids, we can go all the way from a pure IL, so some continuous network of charges, to adding more and more solvents where we might start getting the formation of ion aggregates, maybe, you know, triplets, you know, contact ion pairs, solvent separated ion pairs, all the way to free ions. So let's see what this looks like based on the NMR measurements and our estimation technique using the viscosities. So there's not nearly as much data available in the literature as you would expect for the NMR stuff, but here's one case with imim ethyl sulfate, but it's not over a very wide composition range. And for this composition range, it looks like it doesn't change very much with composition. So the x-axis is mole fraction of water. And so the question is, what happens when we do this with our viscosity measurements? And when you do it with viscosity measurements, we get quantitatively the right numbers, and we get that it doesn't really change with composition of water. All right, but here's a few more. So this is the imim methyl sulfate, imim methyl sulfate, and imim ethyl sulfate. And here now I'm showing you data kind of across the whole composition range, and the filled in symbols is using the viscosities, and the open symbols is using NMR. So you should compare the red and the red, the green and the green, the blue and the blue. And so I'd say in general, I think that our estimation technique with the viscosities is probably not quite as good as it is for the pure ILs. But nonetheless, it does seem to be reasonable. And so we could at least look at trends as a function of composition and with different functional groups on the ionic liquids. All right, so here's water, and dialkyl or ethyl methyl imidazolium with different anions. So the first thing that you're going to see here is, I don't know, what is the first thing you see here? First thing I want to point out is that the chloride is much more dissociated than the others. All right, and that probably makes sense. The other thing is that when you look at all the others, all the way from pure IL up to about 80% water, the dissociation doesn't change very much. But boy, above 80% water, it really changes. And it appears to decrease and then increase. Now, increasing as you get very, very close to pure water, increasing as you get very, very close, that makes perfect sense to me, right? So as we head towards infinite dilution, I would expect everybody to become solvated and the dissociation to go to 1. So that makes sense. But what is this decrease thing? So actually, some of the data that I showed on the previous graph is data that we took in our lab because we're very curious about what's happening in this dilute IL region. So we took a lot of data. And so of course, this is density, viscosities, and conductivities. So here's an example this is the EMIM trifluoroacetate, ethyl sulfate, and triflate. And so these are viscosity measurements. And then on the right are conductivity measurements. All right, so viscosity, obviously, as we add water and we're adding a less viscous thing, the viscosity goes down. All right, the conductivity, this makes sense too, because as you go to no salt in the water, so pure water, the conductivity goes to 0. All right. The conductivity is whatever it is for pure IL, but as you start adding water to it, you're reducing the viscosity. So as you reduce the viscosity, the conductivity goes up, all right? Until you get to a point that you're reducing your number of charge carriers so much that even though the viscosity is going down, the number of charge carriers is going down faster. And so this is why the conductivity starts going down and heads towards 0. Okay. So these are just the same thing. This is the ethyl sulfate, but at 2 temperatures. And you can see we get pretty much the same thing. Now, the graph on the right is just a blow up of the dilute region. And you can see it looks like it's going down and going through a minimum at about 98%, something like that, 98% mole percent water. And so what is going on here? Well, the reality is we are calculating this ionicity, this dissociation, right? Assuming a constant ionic radius, all right? And using that concept, from Unifact. So using a constant radius, it appears that the dissociation is going down, all right? We are not aware of any NMR measurements in this composition range in order to get those measurements. We see this for everything that we measure when we do these measurements in this composition range. And why? Well, we think the problem is the radius, that the effective size of the diffusing species is not constant. So you can go to the other extreme and assume that the ionicity, assume the ion dissociation is constant and back calculate the ion radius. And if you do that, if you assume that the dissociation stays constant as a function of composition and calculate those radii, then the radius starts increasing. So what does that tell us? that tells us either that the effective diffusing species is carrying more water molecules along with it, or another possibility, which actually has been suggested by other researchers, is that you start forming aggregates. So you might be triplets, so that it's a charged species that's diffusing, but it's so uncomfortable in the water that it wants to keep near another ionic liquid until you get really, really, really dilute, when all the all the cations and anions become dissociated. So we believe that this is a reasonable explanation for what appears to be a decrease in the dissociation, but it probably isn't an actual decrease in dissociation. It's a change in the size of the diffusing species. All right, so the last thing I'd like to mention is what happens in solutions that are not water. And so in this case, if you have solvents that don't have a sufficiently high dielectric constant, then they cannot dissociate those salts when they're dilute. So in those cases, you have something that has a certain dissociation when it's pure IL, but as you add that low dielectric constant solvent, in this case, we got chloroform, as you add that, the fraction dissociated just goes down, 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 down until it's zero, basically, as you go to infinite dilution of the IL in the chloroform. So chloroform has a dielectric constant of 4.8, all right? And so this compares both the NMR measurements that are available for these systems and what we estimate from the viscosities. So you can see they're actually in very good agreement as what happens in these low dielectric solvents. Here's some guys in acetonitrile. Dielectric constant is of acetonitrile is 37. So it appears that it's actually able to dissociate these ionic liquids at infinite dilution. So you can see that we get what appears to be this decrease in a minimum in the dissociation, and then an increase as we go towards infinite dilution, just like with the water. Once again, this apparent minimum in the ion dissociation may well be this possible aggregate or formation in the dilute region, as I suggested for the water results. This is kind of interesting. These are this lactone, which has a dielectric constant of 41.7, and a series of dialkylamidazolium bistriphlamides. And you can see that for the methyl-methyl and the ethyl-methyl, they start out with the pure IL is about 80% dissociated, and then decrease. But there's a big jump down when you go to the propyl-methyl. So much less dissociation with the propyl-methyl. So apparently a very clear distinction between the effect of the alkyl chain van der Waals interactions between the ethyl and the propyl, at least in this dielectric constant solvent. This is that same lactone, but comparing the dialkyl to the trialkyl, where you block that acidic hydrogen on the C2 position, and clearly that has a very big effect on the ion dissociation, right? So when you block that C2 hydrogen, your dissociation decreases. Let's see, here's the same IL. So this is a dialkylamidazolium hexafluorophosphate with a series of different solvents of different dielectric constants. The water one, there's not data for the whole composition range. So with water, it's only up to about 20%. But the rest of them, you can see you go from acetone at 20 down to the chloroform with 4.8. And you can see all of these decrease dramatically with their dissociation decreases dramatically as you make it more dilute in the solvents. It looks like the acetone and the pyridine might be able to solvate this IL, all right? But clearly for guys with dielectric constants below 10, they are not able to support solvation in order to dissociate this IL at low concentrations. Similar observations here for another ionic liquid. This is a tetrafluoroborate. Water dissociates it, right? But in both the dichloromethane and ethanol, even though the ethanol has a higher dielectric constant, both of those appear to be going way down in dissociation as the IL becomes more dilute. Here's the temperature effect. So this is in that lactone dialkyl imidazolium bisterfluoramides, and you can see both the as a function of temperature, you know, the 3 different blues or the 3 different greens, the 3 different reds, or the 3 different temperatures for each of these, that there's very little effect of temperature on the dissociation, very similar to the pure IL case. All right, so the last thing I want to mention is that we did some measurements of aqueous dialkyl chlorides, right? So the chlorides are very dissociated. Wanted to see what the effect of the alkyl chain length was on it. And you start blindly taking your density, viscosity, and conductivity data and churning out your ion dissociation, and your values go way above 1, which of course makes no sense. And what's happening here, and it's known in the literature, that these guys in water, as you increase the length of the alkyl chain beyond butyl, you definitely get the formations of micelles. So I like it that the numbers, if you just use the densities, viscosities, and conductivities, those numbers will tell you that something else is going on. Wake up, pay attention. In this case, it's micelle formation. So that's really what I wanted to share with you today. So I think that ion dissociation in ionic liquids and ionic liquid plus solvent mixtures is important. It determines physical properties for key applications. Obviously, this is very important for electrochemical applications where you'd want to be evaluating an ionic liquid or an ionic liquid solvent system. I think that the method using just density, viscosity, and conductivity is actually pretty darn good, better than I expected. And so I think it's definitely a quick way of estimating the ion dissociation. And we've demonstrated that for the pure ionic liquids, the aqueous ionic liquid solutions, and the non-aqueous ionic liquid solutions. That you can definitely use this as a tool for choosing, at least initially choosing what ILs or IL mixtures that you want to investigate for a variety of different applications. And as I said, this work is all done by Oscar Nordness, but with the sort of the idea of using the Stokes-Einstein and just using viscosities, originally coming from Luc Simoni, who, as I mentioned, was co-advised with my husband, Mark Staher. And Luke's now at Chemours. And with that, I'd be happy to try to answer any questions. Oops, escape. Okay. You guys still there?
You, John. Thank you,
Professor John, from the amazing for the amazing presentation. We're now open to question. Anyone can write in the chat or open the microphone and speak. Also, viewers on YouTube can write there, and we will read here. So I think Silvana Mated is going to ask the first question. Do you have your microphone, Professor?
Yes, I do. And I can put my camera.
Please.
I can put my camera. It appears as Tomás is not Tomás. Tomás is my son that used my computer. And today I saw that it wasn't his name. I have to change. I do have a question on what happens on mixed solvents. For example, acetonitrile and water do have are completely miscible, but with an ionic liquid, they have a salting out effect. And of course, one of the phases does have some kind of acetonitrile. It's not pure acetonitrile. The other is almost pure water, but it's mixed both phases. So the question is, you tested mixed solvents, and because dissociation may be important in the system is used to separate biomolecules, so dissociation may be important. And the other question is if you tested in ammonium and carboxyl acids, the ionic liquids formed by ammonium and carboxyl acids that are normally called protic, and they do have more dissociation than the others, or less dissociation. So how dissociated is it?
Yeah, all right. No, okay, so the first thing is you're pointing out the importance of mixed solvent systems. So IL plus mixed solvents. We did not look for data on densities, viscosities, and conductivities for any ternary mixtures. And I think you're making a really good point, Samana, that the dissociation there it probably plays a really important role. So I don't know if there is a lot of density, viscosity, and conductivity data for those ternary systems. Certainly, it would be easy to take that data.
Yes, it's not common to have the data, but actually, I have done some curves on acetonitrile water with ionic liquids, but I do not think about measure the density and viscosity for these systems, and obviously we can do that.
Yeah, I mean we can do that, and actually we actually got a robot to make mixtures, right? And so I think that's a great idea, that we could make up a bunch of the mixtures that are relevant to the systems that you're talking about and measure the viscosities, densities, and conductivities, which is, like I said, all fast and easy, and try to calculate these ion dissociation and see how if it changes as you add the second solvent, if you will. So no, I think that's a fantastic idea. So I'll let you know the results. Yeah, and if you could send me an email with a suggestion of some of the systems that you think would be the most interesting, we could try.
Yes, I can send some data on what we use it for, but we use more. Ionic liquid scolines and also ammonium carboxylic acids.
The ones, right? All right. So that
we are interested in biomolecules. So imidazole, some of the imidazole is not that good for.
So we in this review article we did not include the protic ILs because we thought that might be a bit more difficult to explain or more complicated, and the amount of work for just doing products was huge. So,
Yes.
right. So, so we didn't do the products, but yeah, that certainly would be interesting to do as well.
Okay. Thank you.
Okay. So there is one question from YouTube. It says, do you think is it possible to use this method to evaluate dissociation in deep eutectic solvents as their composition is close of ILs?
Yes.
Okay.
Absolutely. Now I've been in correspondence with some folks who are interested in putting together a database of deep eutectic solvent properties, right? I mean, we got all these ILs from IL Thermo, right? I mean, we downloaded all the data from IL Thermo. Now there are deep eutectic solvent mixtures in IL Thermo, but it's not nearly, as far as I can tell, it's not nearly comprehensive. So for the deep eutectic solvents, I think the first step is the data curation, right? Collecting the data. So, but yeah, answer is absolutely yes.
I have a question.
Robert.
Oi. Congratulations, Professor John. Good to see you again. Last time, I think it was 20 years ago at COP, something like that.
Okay, so this is the benefits of COVID. I get to see you.
Yeah, but the topic is always challenging, and the image you gave us brought me to mind. If you could share with us some of your opinions and some of your thought about what would happen in a solid state. Suppose I have two kinds of systems. One can be a polymer obtained by polymerization of monomers, which are ionic liquids. And then I'm thinking of this polymer swelled in an organic solvent. So the question about this system is, can I still think of ion pair formation in the way you described? On the other side, suppose I have a polymer, a common vinyl polymer, say, impregnated with an ionic liquid. Again, can I think of maintaining the same ion pair you would have only in the solid state? So my question obviously is related to some research we're doing on membrane separation using this system I'm describing to you, either gas or liquid. But again, it's very important to have a better understanding what we are dealing with. So if you can give us some of your thought about it, and again, if some of the experimental techniques you just comment could be useful to identify what really is going on. Thank you.
Yeah, so you brought up some really good questions. And we have just started to think about these. Our first, of course, we just have to keep that the activity of any species in the membrane has to be equal to its activity in the solution at equilibrium, right? And my understanding is that for ion exchange membranes, there's various models for this, like the Donnan model and stuff. Our first attempt is actually not with ionic liquids, but with inorganic salts by estimating the dissociation of inorganic salts in an aqueous solution by this density viscosity conductivity method. We're actually able to better get a better measurement or estimate of the concentration of the ions in the ion exchange membrane. That's just our very first little step in that direction. We haven't published that yet. that we're working on. But then extending it to, the poly-IL solvent mixtures and the polymer supported ionic liquid membranes. I think that all of this will be affected by the ion dissociation, but how to incorporate this ion dissociation into those models, I think we have some work to do. But yeah, no, you're exactly where our thoughts are headed, but we haven't gotten there yet. So,
okay.
Thank you. Thank you for your question.
So I think Professor Haji is the next.
Thank you, Professor Brennecke. I have two questions. One is, we keep using Jones-Dole model for dynamic viscosity, calculating dynamic viscosity of solutions. The question is, the square root term, A term, is usually you can calculate from conductivity, some possibility exists. But the linear term, you can estimate, as you said, from NMR or even your other viscosity measurements. They seem to be quite different. What would you recommend if you want to calculate dynamic viscosity using this Jones-Dole expression, which is popularly used? There's a A term with a square root of concentration and a B term with a linear concentration.
Yeah, I mean,
relative viscosity.
Right. I actually can't say that I've looked at, we haven't done any work on the models for the viscosity as a function of concentration. We've been just looking straight at the data. So I really don't want to say anything because we just really haven't looked at it. So the answer is I don't know.
The other clarification I want to ask is this. From what you said in the beginning, at least in room temperature ionic liquids, the ions has a cluster. I mean, there's no free ion as such. Every ion, you said, is surrounded by opposite ions. So does it mean that is there solvent interaction, is any importance if you conduct any reactions in room temperature ionic liquids?
No, but I mean, even though room temperature ionic liquids, pure ionic liquids have no solvent, they still conduct, right? So there has to be free ions.
You feel that?
So
because
yeah,
every ion is, you said, is surrounded by the opposite ions.
But
from the cluster,
that's all that's
apparently it's bare or solvated. It doesn't make only semantic.
I mean, it's not just, for me, it's not just semantics because, they cannot be hanging. Okay, maybe the answer is it's a time scale thing, right? I mean, you're looking at it, a static picture, they're surrounded by the opposite ion, right? But as a function of time, they move independently. So some fraction of them, 60% or something, 40% move independently as a function of time. So it just means that the ion pair lifetime is sufficiently short that they do still conduct.
Okay. Basically, this is what I wanted to ask you about.
Okay.
Thank you very much. And how expensive are these ionic liquids? Here we have a tough time finding something or buying or you should make them all yourselves.
Oh, we make them all ourselves.
Okay.
Yeah, I make them all myself. But, in this case, we were just taking density, viscosity, and conductivity. Most of the stuff I showed you, we were taking it from the literature. So we didn't have to make anything.
Okay.
So.
Thank you then.
I think it's Richard.
Professor Richard, do you have your microphone?
Yes, sure. Hi, Joan. How's it going?
Hey, how you doing?
Very good, very good.
You're not in Brazil.
Well, I was supposed to be, and then COVID hit.
Next year.
Yeah, hopefully. But I noticed Professor Gubbins seemed to be raising his hand a minute ago. If he wanted to go first, that would be fine with me.
No, you go ahead, Richard. My question's not that important.
Oh, okay. Well, mine's pretty simple. You showed a slide where you had ion dissociation on the left axis, and you had Camlet-Taft beta parameter on the right-hand axis, and you didn't really mention much about that, but it looked like there might be a correlation between the dissociation and the beta parameter.
Right. So that was the one where it was the different anions, right? So the more basic the anion, the less dissociated it is. So, right. So more basic anions associate more with the cations.
They associate more or less?
More, right? If you're so the dissociation is less, right? If the anion is really basic, it really likes the cation. They don't want to come apart.
Okay. But it looked like the correlation went to higher dissociation with higher beta parameter. Or maybe I looked at the graph wrong.
Yeah, maybe I looked at the graph wrong. Yeah, that shouldn't be the case, right? Here I'm looking at it. So, right. So the more basic, I may have this plotted wrong. Oh, the polarity word shouldn't be there. So the acetate is the most basic, right?
Okay.
So it was, so yeah, the acetate was the one which is the most basic, and its dissociation is only 30%.
Okay. So I must have just looked at the scale wrong. Thank you.
Yeah. So acetate's very basic. It's only 30% dissociated, whereas tetrafluoroborate is not basic, right? Much less basic, and it's 80% dissociated.
Okay, I understand now. Thanks.
So, I mean, it actually makes sense.
Yeah, okay.
Yeah.
Professor Gubbs, I think he...
Looks like he stepped away.
Rafael Pellegrino. Rafael, do you have your microphone?
Yeah, I can read my question. Mm-hmm.
Okay.
Okay, do you hear me?
Yeah.
Yes.
Great. Thanks very much for the presentation, Professor Brennecke. I enjoyed very much. My question is, we see many groups around the world modeling ionic liquids with Cosmo-based models, and some report that better results are seen when they model the ionic liquid as an ion pair with a fixed relative position. Seeing your results, would be fair to say that that is just pure chance and compensation of errors, or I would say that, but I'm not really sure.
Yeah, okay. I think, my group also uses Cosmo-based stuff, right? I mean, we published one on the aromatic aliphatic liquid-liquid equilibria, and, we're using it to, screen possible ILs for having LCST behavior and stuff like this, right? So, I'm among the people you're talking about, yes. So, but boy, I think it's exactly as you said, that that one really shouldn't make any conclusions about, oh, it's better if we use, when we use it as an ion pair as opposed to separate cation and anions. I don't think one should make any physical insight conclusions on that observation. As you said, I think it's chance, cancellation of errors, right? I mean, for me, Cosmo is a great screening tool, right? But I That's all I should
Thanks.
say.
That's my feeling too. So just wanted to hear your opinion. Thanks a lot.
Professor Kate Gubbs.
Yeah, I had, this is Keith Gubbins. I don't work in this area, but I had a question just for my education here. I presume you've run across this concept of the Z bond in ionic liquids, and I wondered if you were familiar with that. If not, it's an idea from a professor in Beijing named Shoujiang Zhang, and he's making the point that in ionic liquids, the big difference from simple ionic materials like potassium chloride is that now you've got to consider the dispersion interactions between these much bigger ions. And so he comes up with this concept of the Z bond. So whenever I see him, he's always talking about the Z bond, and I didn't know what on earth it was, but it's some idea that comes out of quantum mechanics, some simple quantum mechanical model. And I wondered if it was helpful. And if you say you don't know about this, then I know the answer, I suppose. But
well, I mean, I don't know about this.
Okay. Then you probably answered my question.
Well, I don't know, but maybe I should go read what Shoujiang Zhang is saying and see if it makes any sense to me. I mean, obviously, the idea that dispersion interactions can be more important, is true, right?
Yeah, that makes obvious sense.
Yeah, but I'm not familiar with what he's describing in terms of the Z bond, so I'll have to go look it up, Keith.
Okay.
So.
Okay, thank you.
I think you have
We're out of questions.
I have one or two questions.
Go on.
Well, Joan, you talk about aggregation and ion pair. It seems to me sometimes you try to differentiate these two concepts. Is it true? I don't know if I'm clear, but sometimes you say ion pair, sometimes you say aggregation.
Yeah. So when
the other time you said methylization, but I think methylization is something different.
Something different, yeah.
Yeah, aggregation in ion pair may be a very, very huge correlation between these two concepts. I don't know if I'm
well, okay. So for me, ion pair is one cation and one anion.
Okay.
Right. And when I say aggregate, I mean something more than that. So, one anion and two cations, or one cation and two anions, or right. So, in my mind, but you're right. But no, I don't know that there's a correlation, because I think in the very dilute region, I think we're getting aggregates, as in more than just one anion and one cation. But over in the more concentrated IL region, I think, I don't know there's any evidence of aggregates. Well, so, I don't know. I shouldn't be talking about this. I shouldn't be saying this.
If you say that aggregation, maybe you have a distribution of size, and ion pair, you will think about a pair of a very sharp distributions, only pairs. Is it?
You're right, and it's a distribution. So yeah, so maybe I should think about how I'm thinking about it, right? Maybe I shouldn't have such a clear thing in my mind of one cation, one anion versus everything else. So
okay, I'm very surprised that when you put water, you didn't see any very strong difference in dissociation, at least in some amount of water. Like you put 6% of water and and have seen no huge difference. So it's very, very, very surprised for me. Even though we know that van der Waals interactions play a very strong role in this kind of system, and I expect some hydrophobic interaction effect. So it's very strange for me. Maybe you have hydrophobic, and at the same time you have increase of dielectric constant. I don't know. So kind of two phenomena.
Well, one thing is that the place where, so the ion dissociation appears to be pretty constant all the way up to about 80% water. And 80% water in most ILs, I think, is about the percolation limit, right? Where it starts busting up the continuity of ILs. So maybe it has some association with that. I shouldn't use association, some correlation with that. The percolation limit of the IL in the system.
Yeah. It's very surprising for me, but I love these results. My last question is about the modeling, very simple model that uses Stokes-Einstein model. I think it was too simple, but surprisingly, it's very nice. When you put water, the size is expected, the size of effective size of the ion change because the hydration. But it's not only that. The Stokes-Einstein is spherical particles, for spherical particles, and you are far from spherical particles. So it's very surprised that it works.
Yeah, I gave a similar talk to this one in the chemistry department. That it was my last in-person seminar back in, I think it was the end of February in a chemistry department, and they were like totally upset about this spherical particle thing. I mean, they were like, "Oh, you got to make them discs, you got to make them oblongs," and I'm like, "Yeah." Yes, you could, but we just did the simplest possible, and it seems pretty good.
Yeah, it's very. My last question is, I promise. What's your suggestion? How we can model these systems? As Rafael point out, I think now after your work, it's clear that all the models, almost all the models are oversimplified to and not taking account this kind of dissociation correctly. But do you think that it's worth to maybe tabulate this constant, equilibrium constant that we're talking about, or the approach that it's more important? What to think about this? What's your suggestion? Feeling, at least.
Well, I mean, I guess my thoughts are that the dissociation, how much dissociated is really actually makes a difference. And if you assume that something's completely dissociated, or if you assume that it's a complete pair, that's a worse approximation than appears to me to be a much larger approximation than even something like assuming that an imidazolium is a sphere. So I guess and because there's so many electrochemical applications of ionic liquids where I think the dissociation is really important. I think that at least for ILs, we should pay attention to this dissociation.
Thank you very much. I love your presentation.
Well, thank you for all the great questions and actually all the great ideas. I wish I had students who could do all these measurements and collect all this data and do it for deep detecting solvents and everything else. So anyway, thank you very much for having me. I really appreciate it.
Thank you.
Thank you, Professor Joan.